Good morning, how are you? I'm all right. Uh-huh, uh-huh. Oh, really, it's not that impressive. That says 10:04. It's 10:07. Make my students not look late. Okay, morning everyone. I know about this time of year it starts to get to the point where design projects are taking its toll already. And the week before. That's an idea Thursday night, as I know and love. So, please join us, don't worry. It seems to have an echo. General things to say about everything. Everything seems to be okay. We're on schedule to finish the tutorial. I'm trying to book the room this afternoon from 3 o'clock upstairs. I haven't had it confirmed. Apparently they're changing all the window blinds, which when it's 3 o'clock in the afternoon in Manchester in a winter's day doesn't really need to be there, but anyway, that's what they're doing. Why are they changing window blinds in the middle of the term? You guys see, I don't know. So I'm going to confirm the room at 2 o'clock, all right, all being well. That saves us walking down the road if it starts throwing you down. Otherwise, you can always walk down the road and go to the JCB 4th floor like we did last week. Thank you to the 70 souls that turned up for the tutorial last week. Thank you for that. I will post the answers up on Blackboard. They are all examination questions. So remember that all those tutorial problems, with the exception of the rung cutter that you're going to do today, or at least see today, along with other questions, I wouldn't set a rung cutter in an exam, it's too boring. And it takes too long. So just be aware that all the tutorial problems that you do in the tutorials are past examination questions. So just remember that. So now, we're building up to the point of parametric sensitivity and how when things go wrong, engineers can design things, but they don't always see everything in their design. So an adiabatic reactor, remember, is one that is left with its own devices. So you set the reaction going, you might need to kick-start it. When you kick-start it, then you set the thing going, and it goes under its own steam. So if it's exothermic, then it will rise in temperature, and you hope that your safety protocols are sufficient to cope with it. So, in the case of what we were studying last week, if you remember, just briefly, we were looking at the isothermal case, and we had equations which linked the heat and the conversion in the reactor. We were looking at an element like a plug flow reactor, except now all we've done is add packed bed. So that element is still the same as the plug flow reactor, reactor, and we're moving through the bed. So the equations themselves are as they were last week, just letting you settle down. And we had, of course, conversion related in an incremental length, that's the Z element, and it's related to rate, which is a function of conversion and temperature and the flow rate in. We're trying to make everything so that you know the measurables. So you've got the temperature in, you've got the temperature where you can measure it, you've got the incremental length, you've got the flow rate of the feedstocks, the molar flow rate or weight flow rate that you can then calculate into molar flow rate in. You've got the mass flow, you've got the heat to reaction, which you should be able to have found from somewhere, and the heat to capacities, so you know what the change in the mixture is as it converts to something. Does it gain heat or does it absorb heat? So therefore, is it an exothermic or an endothermic reaction? And then you've got the rate, which is a function of conversion and temperature over the flow rate as well. So you can see that turns into that. If you look in the handout, you will see that at a particular condition, which is at no conversion, so right at very early temperatures and at the start temperature of the reaction, so if you go back to the very initial rate, remember we like doing initial rates because it simplifies everything. So right at the very beginning, when T equals T naught, the set temperature for the reaction to start, XA equals naught, and you have a straight line, irrespective of the kinetics. So the nice thing about an adiabatic reactor is you can drop out a series of constants. You could say you could drop out the whole function, say it's a number, and that's your fiddle factor, but you will also have the ability to check. Now, some of you will be looking up some thermodynamic parameters within design. Have you come across the Bible, which is by yours, YAWS? Has anybody been referring to that textbook for looking for thermodynamic data to calculate equilibrium constants, for example? YAWS. Yours. It's in a hard copy and there's probably electronic. You can find lots of things on the web, I know that. But you'll say to yourself, oh, I can find this molecule. And I can get parameters on that, but I can't find one for that, let's say. Well, yours is a textbook that might allow you to find additional information if you add in carbon lengths. One of the things that's coming back from the design project leaders is that you seem to get stuck when you're looking for thermodynamic properties. I'm giving you the answer. Go look in yours. Then the next thing you have to do is move another step. And that is, I haven't quite got the molecule I want. I want that thing, but I've got something like that. And then you can start to draw an approximation. If you've got anything that deals with carbon chains, every time you add a carbon number, something happens, and it's usually in a unit of, or a factor of, or a magnitude of. So it might add 10 to the number, it might add 20 to the number, but usually each additional carbon gives you an additional value. Now that, I know, should mean something to Dave Creswell's groups, if any are there. They are here. So Dave Creswell's been going on about that, and he's asked me to send him 4 references on sintering and metal particles. Is that something that you're doing as well? Anyway, so we'll come on to catalyst deactivation. It means nothing to you, worry not, it's coming later. So, I'm just trying to say that the course is hooked in, but the things you can ask me about design projects as well as about my course, because the design leaders feed in. Carlos varies from spitting feathers, which means he's angry, to he's very calm and very praiseworthy of you. So he alternates a bit between up and down. And Dave is very complimentary of his groups, as always. So, what I'm trying to say by that is, when you start your reaction, you've got your initial position, you set everything to the start point, you will get a straight line because it's going to have an adiabatic temperature rise, which is due to the heat of reaction and the heat capacities that you've got for the system, which helps simplify everything. So look at the really complicated equation at the bottom, but what it really means is, because it's an integral, and because you can make small changes, you can do this mathematically in about 10 steps on an Excel spreadsheet. This Excel spreadsheet that allows you to do that, I'll send you a version of it. It's a bit confusing, because it's written by me, and I'm not the most logical of people, for those of you who know me, but hopefully you'll be able to use it when you come to design project. If you don't want it now because it's confusing, that's fine. You can ask me when you come to model those reactor systems. Basically, all I've done is I've done an endothermic reaction where the temperature drops, and I've got incremental conversion down the there. and I've calculated it just numerically. So it's a numerical integration down the bed, because what is integration? It's just incremental step changes. So look at what the equation is. You want conversion against length. Why? Because you want to look at the publications you've got, and you want to say, at this temperature, I got this conversion. Now I've got my reactor. I want to know, you can't just say, oh, all in. It starts at 0 and I got 50% at the end. You want to go 0, 1, 2, 3, 4, and build up based on your model for your kinetics. And remember what the kinetics are. The kinetics are first order, second order, but usually not that simple, so it will be additive orders. So think about Langmuir-Hinshelwood and think about power law. Okay, so I've given you some hints that will help you with design project, because you're approaching these things. At the moment, you're still doing a reconnoiter. You're looking at what's sensible, what's feasible, what's new, what the design leader is trying to point you towards. Those of you with Dave Creswell will, for example, be doing classical oil and gas, because that's where he is. But he will be trying to be innovative, because you've all got sustainability in the title, so you're not at me, if that makes sense. You've got sustainability and something is sustainable processes, etc., etc. Yeah, okay. So, what we're trying to do is just incrementally calculate the conversion down the bed. If it's exothermic, things will go massively wrong quickly. So if it's a large exotherm, when it's a large exotherm, the temperature will spike inside your reactor. The question is, does that kill your catalyst? Does it blow it up, the catalyst and the reactor? Or is it manageable within your design constraints? If it's endothermic, it's not as serious, because you don't generally kill anybody, but it is fairly serious, because if it goes too cold, it turns itself off. So the reaction stops, so you'll get no conversion. So your reaction will either go up rapidly or down rapidly, and what you want to do is make sure you look at that bit in CRE2 notes around parametric sensitivity, because I'm going to touch upon it now in a minute, and then I'm going to show you what happens when it's not designed right. Which is a video clip, which isn't as spectacular as I hoped, because the sound's not working. I'll show you that in a second. Those of you who are in a little bit early, you will have seen the video. So, what else? Anything else to say on that? Everything is within the notes and contained in the words in the handout. You are looking at that equation. What you're really looking at is the conversion divided by the rate with the flow rate in an incremental length. So remember what that equation used to look like. It used to have W over F on the left-hand side, dx over rate. That was your second CRE2 equation. Okay, and you've seen it a couple of times. So we're really, that is very familiar. That is additional for the heat effects, and what we're saying is built into that bit, because of the Z length, is the heterogeneous bit. So you've just added something into your plug flow tube, but the basic equation is the same. Okay, so that's the shortcut, and that's the one everybody likes to use because it's the easiest one to do, adiabatic. Why? Because you don't have to control anything. You let it do its own thing if you've designed it right. Now, this is an exam question that's been done quite badly a couple of years or 3 ago. I'm not saying it will be an exam question this year, but it is something you need to know because you're doing designs, and you certainly don't want to design something that blows up. So remember, parametric sensitivity, what does it mean? It means that you're able to control the system, and if you've got sensitivity, it means there's a very sudden change in temperature, either up or down, but the one that goes up is the one that's the problem. So it means for a very slight change in condition, you may not remember, the diagram that I want you to remember from CRE2, for those who didn't do it, that kind of thing, we've got X, we've got temperature, Cerveso up on the web because the Alchemy have done loads of things within their magazines on Cerveso. It's in Italy. Stuart should have covered it in safety, but it's a classic example of not having enough cooling on a reactor when you design it. Okay. And it's a great example of the second point there. Stability, it may be safely deduced that small inadvertent fluctuations in feed or jacket temperature are always possible, which means in an operation it's difficult to control, and without the right amount of control it will be unwise to operate. So in other words, if your design specialist say we're going to run at that temperature, you go no. And you go no because you've done some basic calcs that allow you to tell you whether it's an exothermic sudden increase or it's in a stable region. Now then, people do safety tests in big companies and little companies, and the safety people are generally very well respected, but the people doing the tests are generally thought to be like bookworms because they sit in an office and all they do is blow things up. It sounds very exciting, but they blow very small things up, and it's very tedious equipment, and then measuring over long time periods. So it's very much it's a vocation, I would say, rather than something you would jump right to doing. So, your diagrams are not coloured. They will be, of course, on the website, on Blackboard. But just to give you an idea, so what are we talking about here? We're going to look at the blue line, which I've made extremely blue. So we're operating, we've got a jacket temperature, and we've got a reaction temperature. And we're setting the reaction temperature to 623 Kelvin, and we've noticed in this particular one, it's flat, but it goes down slightly. So in A, there's a mild reaction, or little reaction, so little conversion, and actually the jacket is cooling the reactor. So it's actually cooled it down to 600, so it's totally safe, but it's not giving us a hell of a lot of conversion. So look at what you're looking at. You're looking at reactor temperature down the bed versus reaction conversion down the bed. Here's the bed length. So we're moving into the reactor. So we're just looking at the blue line. So it's safe. We've operated, it's safe, and we've got a little bit of conversion. But obviously, it's not what we want. So we're going to increase the temperature a little bit. So we're going to try not to cool it quite as efficiently. So we're going to let the bed temperature rise, the green line, by reducing the cooling slightly. And the green line is it's sort of nice. It seems to do its job. It levels off, and then it seems to be stable. The conversion's good. We've gone from about 5% conversion to 30% conversion, so that looks okay. So you would say, well, actually, that's all right. Okay, we'll go with that then. Let's design it. But some wise person should do the calculation again and notice that for 1 degree in temperature, if we go from BC in the diagram, we go from 636 to 637 Kelvin, and something very dramatic has happened. Sure, we've got 100% conversion, so we go, yay. But somebody measured the temperature in the reactor, and it's gone up to 1700 degrees Kelvin. Now we know the temperature of the sun, right? So we're thinking 1700 Kelvin, even if there were the worst engineer in the world that's not thinking, because we've only just woken up, knows that 1700 K is a bit hot. So if you're designing something, and you say, I need to operate this reactor at 2000 degrees Kelvin, you're going, maybe not. What am I going to make my reactor out of? For a start off, was there about, what is the temperature of the sun, 6000 Kelvin or something on the outer surface? I can't remember. Something like that. But it's pretty damn hot, so these are the things you need to be thinking about in design. But here, all we've done is we've allowed the reactor temperature to go up 1 degree. So in other words, we were there, where we had control, and all of a sudden we flipped it 1 degree, and it went straight up to the top. It was 100% conversion, brilliant. But it also went up 1700 degrees. Well, not 1700, but 1100 degrees further. Now then, when put in an exam question, with 2 lines to consider, nobody could explain that properly. 2 years in a row. And that's a fundamental weakness of a chemical engineer, if you don't understand that concept. So remember what I said about the Lange-Hinchman and all that? You're looking for the one that's the rate determining step, the slowest step. That scales everything. But you're also looking for something that might be a bit hidden from view. Is there a secondary reaction that's exothermic? Is there a secondary reaction that's really endothermic that's going to chill everything off and the damn thing stops? So part C. The red one is definitely a no-go, but the pink one, if it is pink, it's a funny looking colour, but it looks a purpley pink, is a no-go as well. And the reason it's a no-go as well is because you've got a spike within 0.2 of a metre of over 1700 degrees Kelvin. Are we okay with that? I've done it slowly. It looks sensible. You all nod at me usually that you understand it. The key thing is to go back and look at your graph for an exothermic irreversible reaction, let's say. Because you know what it looks like if it's reversible, it curls off. Now that's for the benefit of Dr. Creswell's groups will not identify one group or the other group because they didn't quite know what a reaction profile would look like for an exothermic reaction that was reversible. That's an irreversible one. So no matter how much heat we put in it, we increase the conversion until we get to the thermodynamic equilibrium or we get to 100% conversion. So that's an endothermic. An exothermic does what? It comes back down. Correct, young man. Yes, he did the right shape. Thank you, both of you. Okay. So, the last point is parametric sensitivity. Let's not start talking, but let's just hold fire. I'm hoping I'd already opened it, but I've stolen this. So, about 12 months ago, almost 12 months to the day, Jiawei Wang, who now works at Aston University, came and got a job here. And he was brilliant and I love him to bits, but for personal circumstances he needed to move a bit further south, so he's moved a bit further south. He's a really lovely man. So the flash came because light travels faster than sound, and then there was this big bang. That's somebody's house camera that just happens to be pointing into the distance that picked up a large flash and a bang. We've got the cooling towers here, right? One of whom was the chemical engineer that built it. It's 2009, which is not a million years away. It's within your recent lives, maybe even close to being in your degree, just about your own foundation studies. If not, doesn't matter. 2009. How big was the reactor? Do you think? It detonated with the equivalent of 1,400 pounds of TNT. That camera is, I think, either 5 kilometers or 5 miles away from the explosion. It's always amazing when I do anything with safety. I do not understand how you can teach safety on people who were in the past. I know Stuart's not boring, but you've got your attention. Because the poor guy that built it blew himself up. And he took 4 technicians or 3 technicians with him, and it always gets your attention because this could be you. So the slides are moving by themselves, which they shouldn't do, because Jiawei was brilliant. But there you go, he's giving you the description, the before and the after. And I just wanted it, this is parametric sensitivity, and I'll show you why in a minute. And it's why you do need me, or people like me. You need an understanding of chemistry. So before it looked like that. After it looked like that. 4 people killed, 4 employees and 28 members of the public were injured, and the facility was completely destroyed. How big was the reactor? Was it 1 meter cube, 5 meter cube, 10 meter cube, 25 meter cube? Do you think? You saw the flash, you saw the bang? How big was it? Well, he asked the question in his interview, and I went 1, because that's obviously that's what he said. Right. 5 miles away, blew up the site, killed 4 people, and this was a well-built reactor. There's the reactor site. That's the railroad. right? The dots, which you can see, are the injured. Can you see the black dots? That's a bit of the reactor that landed on the road over on the railway track. So that's the side of the reactor. Let's assume it might have been a 5 meter cube, but it certainly opened up, and it's certainly there. These are the dead people, the black spots. These are the injured people. You can see how far they were injured. Look at this, look at this. That's the agitator shaft. That's in the road. So that's the thing that you look at when you're in the Morton lab, and it's that little cuddly little tank with a nice perspex screen with a little twizzy thing in the middle, the agitator. That's the thing that they were stuck on. That's the trucking company trailer that was left in a bit of a disarray. So, it's one of those things when you're playing football and somebody kicks the balls and you're Viking statistic, everybody turns around and goes, oh, thank God, and starts laughing. It just happens. Yeah, it's just what happens. Well, to chemical engineers, this is your equivalent. You know, because you're all sort of laughing, but everybody's thinking exactly the same thing. God, I hope it's not me in 3 years' time. God, I hope I never make a mistake that costs anybody their lives. That's good, because that shows that you actually care about what you're doing. Anyway, I just want to stop his automation. So, it was a very innocuous bit of chemistry. Yes, that's a complicated material. You've seen those things maybe when you were doing biology at school. And you know, compounds like that are used to make catalysts similar, not the same, but you know that hemoglobin has sort of a ring structure. The heme structure starts off going into rings like that, and it traps an ion in the middle. So this is known as a homogeneous catalyst, and it's a manganese center, so it's an active center. And that's what it looks like. Just a nice thing. It's used, worryingly for all of us in the room, as an additive, as an octane enhancer. So you're going to drive a BMW or something with a high performance engine, it might be something that's added. So it's built on chemistry like this. And I don't want you to write it down. You don't need to. The slides will go up on the blackboard side. I don't want you to remember it. But there's 3 bits. A metallation, a substitution, and a carbonylation, which means we're sticking CO groups on this function here. Now then, hopefully it'll pause and it won't move. If it moves, just tell me. That's the reactor. It looks pretty straightforward. It even looks like the damn thing in the Morton, in the James Chadwick building, right? So those of you who've looked at the Perspex thing or are about to, you've got the agitator, the 2-bladed agitator, which you play around as an experiment. It's got a capacity, 2,450 gallons because it's a state, or about 10,000 litres. It's got a vent. It's got a 4-inch rupture disc set to 400 psi. So 400 psi G, we're 15. So that's about 20 bar. So you've got a steel vessel enclosed with a cooling system. Note the cooling system. Okay, so it's internal. It's a tube internal. So it's not a. It's got 2 types. It's got a jacket, and it's got a hot oil thing to cool it. So it's got a jacket on the outside to cool. So it's just like Sevator in that sense. It's jacket cool, and it's got a heating coil to kick it off, to get it going, because of course there's 3 different steps, so different things doing different things. And it's got a vent. Note the bottom. Cooling water going in. Cooling water, 2-inch city water service supply. Control valve, cooling water drain, and manual bypass. Now then, before we say why it blew up, it looks all right, doesn't it? Pause it. So he's filled. Oh, bless him! He's even got an animation filling it up. So we filled it up. We've got it cooking. We've got it started. The process fed the mixture, which is done with diethylene glycol into the reactor. Okay, he added. An operator adds sodium metal through a 6-inch gate. Now, does everybody know what sodium metal does when it contacts water? You remember that at chemistry? Great fun. Urchins living in Manchester tended to nick it from the school laboratories and throw it into the ducts, and the ducts go towards it to feed. Poof! Off you go, and there goes the feathers, and that was the duct. Seen that happen. Not been responsible, but seen it happen. So a man is loading in very reactive metal in the top of the reactor, and you're going, really? Does that happen in industry? Yes, it does. Process operator began heating the mixture. 50 psi, 3 bar. Hot oil control at 182. Once the mixture reached 210 Fahrenheit or 98.9 degrees C or 100 degrees C, the the process operator started the agitator. At a temperature of about 150 degrees C, the process operator turned off the hot oil because he doesn't need to kickstart it anymore. Remember, we talk about kickstarting reactions, and then we've gone to the cooling system. So it started it, so it's given it enough to get the exothermic reaction going, so it's now heating itself, and we're saying the jacket's controlling the temperature. At temperature of 182.2, the process operator initiated the cooling control system, and then he said goodbye. So sobering thought. What went wrong? The water main wasn't on. No cooling water. So the system from the mains wasn't there. No backup system. And therefore it just went and ran away and went bang. I think unfortunately for the engineer, they knew they had a problem, and that's why he was on site at the time. So desired reaction was that. It's massively exothermic. Okay, it's not that exothermic. It's 45 kilojoules per mole. 45, yeah, we're doing on time. 45 kilojoules per mole, roughly. So it's a bit lively. So when you're looking at design projects and you're looking at, is it endothermic, is it exothermic, get a scale in your head about what that does. So anything that's 100 kilojoules per mole is going to be massively exothermic or massively endothermic. 50 is quite large, 10 is not large. So if I've got an exotherm of 10 minus 10 kilojoules per mole, I'm going to go, oh, it'll warm up a few degrees, it's not too bad, depending on the total volume of what we've got, but it's not too bad. If I've got one of 50, I'm going to be a bit worried. If I've got one of 100, I'm very worried before I start. But if you just think about that, you'll remember that for design. Those are numbers that are important. 10, not so bad, manageable. Anything a bit more than that, when we start 25, we're starting to worry. By the time we're at 50, we've got to take precautions if it's exothermic, and we've got to know it's not in this runaway situation. So fortunately for me, I've got the temperature, I've got X. Equal and axis, it looks slightly different, but the conversion is also the thing that we concern ourselves with. But it's the rate of change of heat. So he's in a runaway, the heat is generated, and we've suddenly run it away. What didn't they know? Surely they designed it for that, and indeed they did. But of course no idiot designed it. Well, obviously the failure was they didn't put an alternate cooling system on, so there was no cooling. But they also found out it should have exploded. And that is what it should have done. It should have just puffed it out, blown the bursting disc. So that's the reactor test system, that's the test system with the burst cell. It should have just blown the gasket, vented itself, and it would have been all right. That's what should have happened. It was designed to empty its contents through a 4-inch pipe. Well, they tested the system, and you can see what happened. Recognize the curve. You've just seen it, except what you've got there is a pressure curve as well as a temperature curve. You can see that in times in minutes, the system went beautifully and looked super stable, and all of a sudden, between there and there, which is approximately 3 minutes, it went up massively in pressure and temperature, and it went bang, and you can see it on this little old lady's house camera, X number of miles away, and 4 people were then dead. It's the same graph I've just shown you. What they didn't know was they hadn't investigated the chemistry properly, and they only assumed the top reaction was working. Look at the bottom reaction. Doesn't matter whether we understand it or we don't understand it, but they've just added this sodium in there, remember? It gives you lots of hydrogen, and it gave you a 32,000 joules per mole. Okay, 32,000, or is that 320,000? 320,000 joules per mole. So now we've got a 9 times more severe exotherm in a secondary reaction that nobody knew about. The moment the water didn't go off, what they didn't realize was the moment they got to this temperature, that reaction kicked in. They legislated for only the top reaction, and they would never ever go faster than this, and this is the vent rate, and they'd done all the stats, but what they didn't realize was they had a bomb, because this reaction has 8 times more energy released from it, and of course it therefore heated everything up in a split second, and it went bang. This is all there, and I've got the references for you, and you can have a look, and it's quite a sobering thing, but it's a good aspect if you're designing a batch reactor in your design project. You've at least got a nice little model of a particular reactor that you can use. The explosion was a runaway. There was a reaction, the red letters basically, they were completely unaware. The reactant cooling system had no redundancy in it. It was a single point of failure. If the mains wasn't on, it went bang. And they didn't legislate for that. The chief engineer designed the pressure release for the normal operating conditions, but was completely unaware of that 8 times more exothermic reaction. That was it. It was just simply that. Everything was fine. Of course, once the water was off, there was a problem, but it should have just blown the gasket and emptied into a dump. But it didn't, because the moment it hit 190 degrees C, that second one kicked in and everything went 10 times faster, and it just couldn't get out in time, and it was a big bomb. Now, he got the job because of that little presentation, and I've given him due credit because it's his slides. But it makes you think. And your complete silence, I think, is respect enough for the 4 people that died anyway. But if you want to go and look it up and look at how design is affected by it, you can do. The top one is the actual investigation. I'll put it up on Blackboard so you don't need to write it down. But I thought it might help you with the design, and you might look at the safety aspects when you have to do that in the final HAZOPs and everything that you do. So I thought it would help. Okay. Any questions on that? Do we think we now understand a runaway reaction? Do we now know if that exam question came up, you understand the implications because you've had it rammed home? Did I do it better this year? I hope so. Doesn't mean to say it's on the paper, but if you understand it, I've achieved what I wanted. Are we happy with that? Brilliant. I'm looking around and we're not dissatisfied with it, so that's good. There are lots of things that go wrong on plant, but if you instrument them and legislate for the chemistry and the reactor system, hopefully it won't. Now then. I'm just checking the tutorials, that's why there's a slight interruption. Also giving you time to take that in, because I know it's not a very nice thing. So tutorial 5, yes, that's got the wrong cutter in it. Tutorial 6, right, so tutorial 5 and 6 are very important because they've got examples of what we're going to cover. I'm introducing it now. I don't intend doing very much more, so for once we will finish on time or slightly early to give you a chance for a coffee and to let Tom come in on time for once. But this afternoon we'll just go through this, and there's a tutorial associated. There's a run cutter which I suggest you will try to ask the demonstrators how to do it today, and then if you can't do it, and then you can have a go at doing it over the weekend, next week. I know you've got lots of coursework, so that's not necessarily going to be possible, but have a go in your own time. The answer will get posted, but I really want you to do the tutorial associated with this class. Okay? So, now we meet some reactor types. We've had a very basic introduction to the sort of design equations. Now we're going to say, well, how can we pull all this together? We've learnt about the mass transport, we've had some words about diffusion, we've had some words about active site and surface reaction limited. So what does that mean to us? So let's just have a clear definition now of reactor types. Differential and integral reactors. You've heard me say it. Differential, low conversion, integral, high conversion or medium conversion. Recycle reactor you're familiar with. A little spinning basket reactor you might not be. And I'm just setting one of those up to do alkylations up in the lab upstairs. And it literally is a pot with a basket and an agitator. So imagine your setup that you've just seen blow up with its agitator, but now picture between the two blades, picture a basket which has got a catalyst in it. Okay? So it's doing mixing, so it's helping to get the effects of energy that might be released or energy that's being sucked in. It's actually mixing, but the catalyst remains static, but the contents are moving through the catalyst. posh version of a spinning basket reactor is indeed called a Berti reactor. That sometimes is easy to remember. So we'll have a look at that. We won't discuss everything on there, but if we just look at what we should be covering, note that the different bases on which we can get results are, remember that bit, it's always the first half of that equation, second, the two bits which are flow rate in, molar flow rate, times the change in conversion, the rate change in conversion in effect, equals the rate times the difference in the volume of the contents. That would be your normal CRE2. CRE3 then changes that to be the rate times the weight. So that's the equation that helps you calculate the amount of catalyst that you need in effect. As the bases change, so do the units, of course. That does confuse because everybody goes, oh, what is equal that? I can't rationalize my units. Well, of course, what you're doing is you're keeping the FA naught and the DX on that side, and then you're doing it either in terms of a volume, a reacting volume, which meant it was homogeneous if you were second year CRE2. Okay. Now we're talking about heterogeneous, so we've got a fixed powder, and that allows us then to say, well, we need a weight of catalyst. So one of the things you will have to do in design project, one of you somewhere, several of you in your group, will be asked to design the reactor system, and you will have to know how many bugs you need if it's a bioprocess, how many chunks of catalyst you need, or what kind of catalyst you need, how big a particle size, and all that sort of thing, and that comes out of the weight. The surface then starts to break into, well, how big a surface area do we have, and what's our reacting surface, and now we're really getting into something that's my area rather than necessarily what you need to do for design. But you'd certainly be looking at that bit of the equation, remembering that you substitute, obviously, for the common terms. So it's either a volume, a reacting weight, or a reacting surface. That comes more into my domain. We'll leave that. So proper interpretation of reaction rates. A kinetic model and the evaluation of diffusional effects presupposes a proper knowledge of the state of the fluid flow in the reactor. Pause. A deep breath. Right? So we've just seen in that explosion where they didn't understand the chemistry. So they had the reaction geometry, they mixed it, but they didn't know about the temperature, and they didn't know about the second reaction that was going to rise the temperature very, very significantly. But also, you want to know, is everything doing what it should do in your reactor? So you've got to evaluate a kinetic model, try to figure out if it's diffusional constrained, if it's mass transport limited, or if it's surface reaction limited. You want it to be surface reaction limited because then your model's going to work probably. If it's not, you're going to have a problem. So to help you, various types of tricks have been employed. So we tried to do a plug flow reactor, standard thing. You remember I showed you the graph the other week, standard equations, nothing new, nothing that you haven't seen before. Rate of change of the volume of the flow over the rate of change of conversion, 1 over the rate. So we're trying to take a gradient of that graph, in effect, and get the rate. Problem we've got is the data's all over the shop, also it's a curve. Where do we take the rate? At what point are we measuring the rate? And how do we know when we measure the rate it's actually controlled? So you've got to test it, and that's why engineers are always optimizing things. Propagated through all your equations and nothing makes sense. So don't overcomplicate your very first design. Don't try and do things in 100 steps if you can try and do them in 3 or 5 or 10. So in other words, any spreadsheet you write that tries to do a calculation should be done in 10 steps. So if you've got a conversion that goes from 0 to 100, 10% conversion is fine. You should have picked that up from CRE2. But the main reason you want is common sense. Because you can see it on the spreadsheet. So if you put the number in and it gives you X of 0, 1% and it should have been 100, you've made a mistake. No point having 100 sections. So I go, and you do it in spades. You try to go. So if there's 100 units, you will go at 0.01. Where you could have gone at 10. And you would have seen it in front of you and your number would be nowhere near and the error will kick out. Try and keep your design simple. So that when you're doing calculations, keep it simple. A plug flow reactor that's differential is trying to do that for you. It's trying to minimize the conversion. Okay, so we'll look at that. We'll bear that in mind. But why, if it's very slow conversion? Because we can make it numeric. We don't have to have any integrals or anything. We can just say, well, the conversion at the final point minus the conversion at plus the conversion at the initial divided by 2 is an average. That's in fact an integral. So therefore we can plug the numbers straight in there. We can have the flow in and the flow out. That's the molar flow in of the reactant and the molar flow out of the reactant divided by the volume. We've got an average rate. That's so simple, it's not true, but it works. So we try and keep the, how low do we keep the conversion? Well, as low as we can damn well can keep it, but what's the problem? We're at really titchy conversion and we want to be at 80% conversion. So we're here with our little reactor model trying to get kinetics and we want to be over here. We're way away from the design parameter, but it gets some of the important kinetics out, which we can then test if we go to higher conversions. So we start simple, we go more complicated. I'm going to stop there because we can cover that this afternoon, and we're for once on time for poor old Tom. I'll take any questions at the front because we've got a little bit of time for that if you want. Other than that, I'll see you 2 o'clock in here, remember, for those of you who didn't make it last week. 2 o'clock in here, and then a tutorial, all being well, upstairs on D floor so we don't have to walk very far. Okay. Alright, thanks everybody. It's been very good this morning. Perhaps that safety video I should put on everyone. On time. I had to give Jarway's, show Jarway's explosion for parametric sensitivity. So it's quite nice. I never forget to take the stick out. I think it locks it. When it logs out, it logs it out as well, I think. So.
It doesn't really do anything.
Well, it doesn't mind for some reason. If I pull this out when it's not right, it doesn't like it. That's it. It's gone.
I think that might just be that. That
might just be my... Yeah, well, that wouldn't be too surprising, would it? Righty-ho, I shall... He's not going to use that. Right, your collar. I've got my thing. He's logging off. Right.
There's only one. That's one. That's just the same as for like the last 2 weeks. I'm losing my tablet. No, I've already given out 180, and there's only 125 people. Yeah, I don't have any more left because, as I said, I made so many extras to start with.